Welcome class to the Stat 312, Chapter 9, Notes for Factorial Experiments. To start off this chapter, let's do a little bit of recalling. So for Chapter 6, we learned that methodology was presented for comparing means of populations. The populations represented two or more levels of a single factor, and the means were taken with respect to some numerical response variable. So if we think back to the example we primarily used, which was exercise 6.2, which examined the mean response time required for mice to complete a maze with 3 different colored doors. So for our case, our response time had a factor color, and those colors had 3 levels: red, green, and black. So if we're thinking back, we had mice going through 3 different colored doors, red, green, and black, and we were trying to record their response time through the maze. The tools we used to analyze this data was called one-way analysis of variance, also known as one-way ANOVA. Now, in continuing with our recall of what we've learned so far, I'd like to make a chart with you guys, just to kind of visually see what we've learned so far. So to make this chart, we are essentially going to make a 3x3 grid. Oops, my apologies. My ability to draw a straight line is not the greatest. Okay, so continue with our map. Let's make our x-axis as number of inputs slash, whoop, that was my hand, factors. And on our y-axis, we are going to have input type. So to further label our number of inputs and factors, we focused on having one input or 2 or more inputs. As far as our input type, we dealt with qualitative and quantitative data. And oftentimes, we refer to qualitative data as nominal data and quantitative data as numerical. Now, to start off class, we focused on having input with 1 level when that data was qualitative. That was chapters 1 through 4, our review stuff. But when we really got into the meat of the class, we dealt with input with 2 levels that were both nominal, and that was in chapter 5. When we started having that single input or that single factor with multiple levels, that's when we introduced the one-way ANOVA that we learned in chapter 6. Starting in chapter 7 and chapter 8, we moved away from that qualitative data and started looking at quantitative data. So when we had that single factor or single predictor that was quantitative, that's when we were doing SLR, which was our chapter 7 material. When we were dealing with 2 or more factors that were both quantitative, we were doing our MLR, or multilinear regression, in Chapter 8. For this chapter, we're going to go back and focus on this empty square of qualitative data that has two or more factors. And in order to solve this, we're going to be focusing on two-way ANOVA and three-way ANOVA. And strictly speaking, there is higher. We're not going to necessarily focus on it because once you understand two-way and three-way ANOVA, you can easily see how everything else extends. But before we move on to this, I'd like to take a moment and complete an exercise using that rat data from table 6.9, because I want to numerically show you in JUMP how a one-way ANOVA table in Chapter 6 and using those indicator variables from multilinear regression will actually result in the same overall F-test. So let me take a moment and pull up our rat data. So naturally, these two columns here did not come with the rat data. It was just the color and time. But I went ahead and added in our indicator variables. So for color, we have three colors: red, green, and black. So if we remember, for our indicators, we are doing I minus 1. So we have three colors, 3 minus 1, which is 2. So to make these two columns, I did a red and a green, and I let black be that baseline. So whenever we had a color red, I put a 1, 0 otherwise. And for the green column, green was 1, all other inputs were 0. Now I'm going to analyze this data. So if I go to Analyze, Fit Model, start off, I'm going to analyze it using the one-way ANOVA table. So time was our response, and color was our factor. And I'm going to select Run. Oops. Trying to move this over. There we go. And if I scroll down, we can see we've got our summary of fit and our analysis of variance. If we do our job correctly, the summary of fit and analysis of variance should be the same using our indicator variables. So let's take a look. If I go back to our data table and I go to Analyze, Fit Model, time is still my response. This time I'm going to make red and green are predictors. I'm going to select Run, slide this over. And pull up our previous slide and take a look. Does it look the same to you? Looks the same to me. We've got the same R squared, adjusted R squared, root mean squared error, observations, mean response, and the same overall F-test. That kind of just gives you an idea of how we can manipulate the data in order to analyze data in a multitude of ways, because different methods of analysis can give us different pieces of information. So now that we've reviewed material that we've already previously covered and even built some connections among it, let's go back and focus into Chapter 9. Okay, so for this motivating example, let us suppose each of 20 pots was randomly assigned a fertilizer labeled 1 through 4 and a balanced design. Now recall, balanced designs means that we have equal sample size. So if we have 20 pots with 4 fertilizers, that means we've got 5 pots per fertilizer. And for us, we're going to measure the weight of fresh strawberries as our response, because ideally we're going to want to select the best fertilizer that will produce the most strawberries. So by looking at our table, we've got our 4 fertilizers, and then we have these 2 new columns for nitrogen and zinc. These are going to be the two factors that go into our fertilizer. And we can notice that each of these two factors each have two different factor levels that go into determining the effects on our response. So again, we've got two factors, nitrogen and zinc, and each of these factors have two levels. For nitrogen, it's 10 and 20. For zinc, it's 0 and 1. Now, by reorganizing this table so that the rows correspond to the levels of nitrogen and the columns of zinc help our columns to the levels of zinc, this can help motivate contrast of potential interest. You can remember that we learned contrast in chapter 6. But before we get to that, let's review some, or perhaps for the first time, learn about the difference between designed experiments and observational experiments. So if we recall from our discussion in Simple Linear Regression 1 notes, correlation is not causation. So to establish a cause and effect relationship, this can be done if our data source is a designed experiment. This is something that they delve into pretty deeply in Stat 313, Design of Experiments, but we're only going to touch on the surface for it here. Any other data source is commonly or generically referred to as an observational study. In the context of slide 239, fertilizer with N of 10 and zinc of 1 is an example of a factor level combination. Also, or a treatment. Going forward, particularly if you take other stats class, treatment is often referred to as TRT. It's still pronounced as treatment, but that's how it's abbreviated. The term treatment is often reserved for designed experiment contexts, such as slide 239. For example, any pot can be assigned any fertilizer at random. Design experiments necessarily use randomization to assign treatments to experimental units. We're not going to go into much as to why this is. That's something that they focus on in Stat 313. But basically, when you think back to our formulas for our ANOVA model and our linear regression model, you notice how we added that epsilon term, and I kept calling it the error term. Randomization reduces that error term, which ideally is a very good thing. So in our three-way ANOVA example, something we'll look at eCampus, it simply compares a group of people on a stress test. In this context, the three observational factors are gender, body fat, and smoking history. So a female with low body fat who is a heavy smoker is going to be a factor level combination, not a treatment. Treatment is something that we have control over and that we've designed in our experiment. Things that we just see the way things are, that's going to be an observation. And so we'll call those factor level combinations. So continue looking at our motivating example. We have now rearranged our data to have a y-axis with our nitrogen at 2 levels and our y-axis of nitrogen at 2 levels and our zinc on the x-axis with its 2 levels with our factor level means in the center of our charts. So right now, let's talk about how we can have these main and interaction effects on our response. So the overall main effect of nitrogen is going to be y1 dot bar plus y3 dot bar, n quantity, minus the quantity of y2 dot bar plus y4 dot bar. And to show what this looks visually, what our overall main effect of nitrogen is trying to show the effect of just nitrogen, ignoring the factor of zinc. So that means we would be comparing the low level of nitrogen versus the high level of nitrogen. We can do the exact same thing for zinc. We're going to compare our low level of zinc versus the high level of zinc. Or in other words, y1 dot bar plus y2 dot bar minus the quantity of y3 dot bar plus y4 dot bar. Now, to take it a step further, we know that sometimes it's not realistic to look at just the main effects. Sometimes we have something of an interaction effect. To put this into context, say you're training for a swim meet because you're a swimmer. In order to be a good swimmer, you need to have endurance and strength. So what can happen is, yes, we can study just, someone, how fast you can run, how fast you can move in the pool, or we can study about how many weights you can lift. The interaction effect looks at that combination of both your endurance and your strength. So for our case, let's examine the interaction effect of our nitrogen and zinc. So one thing is we could look at the change in effects of nitrogen over the levels of zinc. This would be y1 dot bar minus y2 dot bar, n quantity, minus y3 dot bar minus y4 dot bar. Or we can examine the change in effects of zinc over our levels of nitrogen, which would be y1 dot bar minus y3 dot bar, n quantity, minus the quantity of y2 dot bar minus y4 dot bar. However, what this really boils down to when we're trying to see this interaction effect is comparing our nitrogen and zinc at, say, we have our zinc and nitrogen both at the high level and low level, and then we compare it to nitrogen and zinc in a combination of high and low levels. Or in other words, y1 dot bar plus y4 dot bar, which is both at our high and low level, and compare it to our combination. So y2 dot bar plus y3 dot bar. So at this time, let's do an exercise to show that the main effects of nitrogen and zinc and their interactions are a set of T minus 1 equal to 3 mutually orthogonal contrast. So let me pull up a blank slide. Okay, so let's make our mutually orthogonal contrast. So first off, we know we have our 4 treatments. Treatment 1, 2, 3, and 4. And these treatments have our response, or that sample or row mean, of y1 dot bar, y2 dot bar, y3 dot bar, and y4 dot bar. And now we can add in our variable columns. So for treatment 1, nitrogen was at the high level and zinc was at the high level. For treatment 2, nitrogen was at the low level and zinc was at the high level. For treatment 3, nitrogen was at the high level and zinc was at the low level. And for the last treatment, both zinc and nitrogen were at the low level. Now taking a look at their dot product, we can multiply. After we finish our multiplication, to check if they're contrast, our summation of our contrast should equal 0. So, adding up our nitrogen column, we've got 0. Our zinc column, 1 plus 1 minus 1 minus 1, 0. And for our dot product, we also have 0. So that means nitrogen and zinc alone are contrast and their dot product is contrast. So therefore we have mutually orthogonal contrast. Make sure you know how I did this because you may see it on your final exam. At this point, let's circle back to our notes. So we've completed our exercise. So now that we've looked at the contrast, let's move on to something called a profile plot or an interaction plot. We use these to visualize the main effects and interaction effects. Definition. For two factors, a profile plot or interaction plot graphs cells or sample means versus the level of a factor with line segments connecting means having the same level of the other factor. So based on our slides for 239 and 241, let us suppose we have this following profile plot. So for profile plots, we have an x and y axis. Along the y-axis, we have that factor level mean. So for now, I'm just going to do a generic of yi dot bar. And then for our x-axis, we have one of our factors. So in this case, I'm going to select nitrogen. And we had nitrogen at two levels, level 10 and at 20. Now, we still have to show our second factor, our zinc. So in this case, I'm going to draw two line segments. I'm going to let the lower line be when zinc equals 0 and the higher line when zinc equals 1. This is one example of what a profile plot can look like. The next question is, well, how do we interpret this? So if we look at this profile plot, we notice that our lines are parallel. Well, for us, parallel lines segments indicate that there's no evidence of interaction between zinc and nitrogen. In other words, a test of a null hypothesis, which would be the quantity of mu1 minus mu3 n quantity minus mu2 minus mu4 n quantity equal to 0, or the alternative, when it's not equal to 0, has a quantity of mu1 dot bar minus mu3 dot bar and quantity minus mu2 dot bar minus mu3 dot bar equal to 0. which would mean if we were to do this in an overall f-test, our f-test would be 0, and we would have a p-value of 1, where we have, and again, this is just in cases when we have parallel line segments in our profile plot. And a p-value of 1 means we do not have a significant relationship. So again, no interaction when we have parallel lines. If our lines intersect or are close to intersecting, that is an indication that we do have an interaction effect. Let's take a look at some more examples of profile plots. So for chapter 9.9, page 509, I believe, if we look at concept question number 1, we are asked to draw an example of a profile plot satisfying each of the conditions below, based on our factors of nitrogen and zinc from slides 239 and 241. So the first part, we're asked to show that nitrogen has a main effect, but it has no other effects. Now, for these parts A, B, and C, you're going to see me draw 2 profile plots. And the reason I want to show you 2 plots is because I want to do 2 situations. One, when we have zinc for the x-axis, and the other with nitrogen being on the x-axis, just to show you how 2 different plots can actually show you the same information. So, drawing our 2 plots. Again, the y-axis is going to stay the same, yi dot bar. For our arbitrary row means, we'll have zinc and we will have nitrogen. Zinc has its 2 levels of 0 and 1, and nitrogen has its 2 levels of 10 and 20. So to show that nitrogen has a main effect when zinc is on the x-axis, we are going to show two parallel lines at n equals 10 and for n equals 20. So in this case, we are showing, because the y-axis is our response, that number and weight of strawberries. So if n has a main effect, that means that nitrogen has an effect on the weight of the strawberries. And in this case, we're going to assume that the more nitrogen means a higher weight. But there's no effect on zinc, so it doesn't matter whether zinc was at the 0 or at the 1 level. It's not going to change that slope of our line. For the other case, when we had nitrogen on our x-axis, we're saying that, that nitrogen had an effect. So that means when it's at its low level versus its high level, we should see a rise in the weight of strawberries. Now, because zinc has no effect, our line is actually 2 lines right over top of each other for both when nitrogen was at 0 and when nitrogen was at 1. And now that finishes part A. Let's move on to part B. So for part B, we are asked to show that nitrogen has a main effect, which we've already shown above, but there is also a nitrogen by zinc interaction, but with no zinc main effect. Now let's think for a second what this means. So for our fertilizer, if we're looking at plot of pots with just different levels of zinc added, we wouldn't see a change in the weight of strawberries. We would, however, see a change in the weight of strawberries depending on the amount of nitrogen we've included. And to show that interaction effect, think that it's showing that, all right, we have all of these pots with nitrogen in them. Now we're going to add different levels of zinc into them, and we are going to see an effect of that. So to show this visually, once again, let's draw two plots. Y-axis is going to remain the same. And same as above, we'll put zinc on the left and nitrogen on the right. Okay, now we're ready to draw our lines. Now, if you recall from slide 242, I said if we have an interaction effect, you should see lines that either intersect or come close to intersecting. So if we're looking at our first graphic, we can see that when zinc is at 0, we have this distinct level for nitrogen at 20 and when nitrogen is at 10. But those lines come and almost intersect. They have different slopes showing that interaction effect. So we can even see how, oops, pros and cons of a touchscreen, how the width at level 0 and at level 1 for zinc is different. Now to show this, when we have nitrogen on our x-axis, we're going to still show that distinct rise of 10 to 20 when nitrogen is 0. But when nitrogen is at level 1, we see how our lines intersect. We've got that interaction effect. And we can see this space. Now notice for this case, we have this space being about equivalent. That indicates that our zinc has no main effect. Oops, and I realized I labeled this wrong. Zinc, zinc. All right, last one. There is an N by zinc interaction, but no main effects. Okay, so look for this. This is probably the easiest one to draw. So do the same as we've done before. To XY axis. Y-axis are the same and slight variations to our x-axis. Now, our lines in the middle are going to be just about identical for both charts because there is no main effect, just an interaction effect. Meaning individually, the zinc and nitrogen didn't have effective weight of strawberries, but together we can see a change. All right, so notice about the spacing of our line segments is about equivalent. That should be the case when we have no main effect, just interaction effect. Okay, so that brings us to the end of talking about our profile plots. Now let's take a look at some more information that we need for Chapter 9. So often a data set and its corresponding analysis concerns more than one qualitative factor. So for example, what we saw in slides 239 and 241. So in order to deal with that, we must expand our one-way ANOVA methods in order to analyze this data directly, meaning we need to estimate study main effects and their interactions of our factor level combinations. So, for example, on slides 239 and 241, Chapter 9 defines notation to convey the two-factor structure of such data, where we had the 2-row, 2-column table on slide 241. This is the preferred way as opposed to how we showed the data in slide 239. So when we are looking at our one-way ANOVA data, we may have had a chart similar to this, which is table 9.2 for data with our motor oil experiment. We had 3 types of oil, and we had 5 observations per type of oil, and then we had our, let me make that a darker color, and we had our row means of, say, y1 dot bar, y2 dot bar, and y3 dot bar. And in this provided example, we can notice that the sample size for standard oil, for multi-oil, and for the gas miser oil were all 5, meaning that this is a balanced design, or we have balanced data. We will focus on formulas for balanced data in this presentation, although JMP can handle balanced or unbalanced data for 1 factor or 2 or more, or any other statistical software you may choose to use. Now let's take one step further and take a look at how data for the two-way ANOVA will look. So essentially what happens is you take your data for the one-way ANOVA and you just add another factor. So in this case, we still have our motor oil with our 3 factors, standard, multi, and gas miser. They still have 5 observations, but what we did is we added an engine type. So we now have 2 engines, a 6-cylinder and a 4-cylinder engine. And because we have these different engines and motor oils, we're going to have more means involved. So for our engine means, we can see that they're going to be abbreviated Y bar I dot dot. So before I go further, let me show what that means. So if you remember from previous, we had things like IJ, where I was this observation and this factor level. So that's going to continue. We just have to add another level. So IJK is going to be each observation. I is going to indicate in this example what engine they're using. J is going to indicate what oil is being used. And K is going to indicate which observation. So for example, Y1, 2, 3, so that's 1, so that's first engine, 2, so that's the second oil, which is the multi, and it's the third observation. So that's going to be 24.6. So again, 1 is the 6-cylinder engine, 2 is going to be the multi motor oil, and 3 is the observation number. Some other little bit of notation. Each of these individual, say standard, it's the all the data for the 6-cylinder and the standard. Each of these are going to be referred to as a single cell. And then so in each cell we are going to have 5 observations. Next, let's take a look at how we are going to abbreviate the means. So, using our YIJ, engine is the first one, so the mean is going to be Y bar I dot dot. I means it's going to show for the different engine types. So for 22.247, that would have been y1 dot dot. And for the 24.8 or 487, that would have been y2 dot dot. For that overall engine mean. We still can look at our cell means, which are abbreviated as y bar I j dot. So for example, if we look at 23.52, that would have been y2 1 dot. Second engine, first oil, and then the dot meaning we have that mean of all of our cells. We can also look at our overall oil means. So for 22.620, that would have been y dot, because it's over both engines, 1 dot, all cells, bar. 23.840 would have been y dot 2 dot bar, and 23.640 would be y dot 3 dot bar. And then our overall grand mean is y dot 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 bar. And again, that's our grand mean or our overall mean. Okay, so not too bad. It's really just an extension of what we've already been looking at. Now let's look back to the way we used to do our ANOVA model for one way. All of this should hopefully be review. So the one-way ANOVA model, something we've grabbed from slide 51 during our chapter 6. If we recall, the fixed effects one-way ANOVA model is Yij equals Ui plus epsilon ij, which was equivalent to mu plus tau I plus epsilon ij. For I equal to 1, 2, all the way to t, and j equal to 1, 2, all the way to n, where Yij equals the jth observed response from the ith population, mu I was the mean response of the ith population, epsilon ij was the difference of response j from its population mean mu I, and we would say that the t times n unobservable epsilon ij are a random sample from a normal distribution with mean 0 and variance sigma squared. So when we extend it to the mu plus tau I plus epsilon j, we said that mu is equal to the summation over I of mu I over t is our overall response mean, and tau I is equal to mu I minus mu, and it is a parameter that measures the effect of an observation being in population I. And of course, those two previous bullets imply that the summation of I equals 1 to t of tau I should, in theory, equal 0. And again, this should all be review. If you're a bit confused on that, I highly encourage you to go back and look at chapter 6. But at this point, let's move on to look at our now two-way ANOVA model. Okay, so the two-way ANOVA model. So two-way fixed effects ANOVA model is Yijk equal to mu ij plus epsilon ijk, which is equivalent to mu plus alpha I plus gamma j plus the quantity of alpha times gamma ij plus epsilon ijk for I equal to 1, 2, all the way to a, j equal to 1, 2, all the way to c, and k equal to 1, 2, all the way to n, where ijk is the kth observed response at the combination of the ith level of factor A and the jth level of factor C. Mu ij is the mean response of the population with factor A at level I and factor C at level J. Epsilon ijk is the difference of response K from its population mean mu ij. The A times C times N unobservable epsilon ijk are a random sample from a normal distribution with mean 0 and variance sigma squared. Continuing on, so mu is going to be the summation of ij for mu ij over A times C and is the overall mean response. Alpha I is the main effects which you'll see me abbreviate as capital ME of factor A at level I. And gamma J is the main effects of factor C at level ij. And alpha times gamma ij is the interaction effects which you may see me abbreviate as INTS, between factors A and C at levels I and J. For our 4 previous bullet points, they're going to imply that the summation of I equals 1 to A for alpha I is equivalent to the summation of J equal 1 to C of gamma J, which is equal to the summation of I equals 1 to A for our interaction effect of alpha times gamma ij, which is equivalent to the summation of J equals 1 to C of our interaction effect of alpha times gamma ij, which is all equivalent to 0. So let's take a look at an example and do our two-way ANOVA model using that engine example from slide 246. So we are going to say that Yijk is equal to mu plus alpha I plus gamma j plus alpha times gamma ij plus epsilon ijk. We'll say where I is 1, 2 are 2 different engines, J is 1, 2, 3 are 3 different types of motor oil, and K is 1, 2, 3, 4, 5 for the number of observations per oil and engine level. So to further define, we have Yijk is the kth mile per gallon observation for the ith engine and jth oil. Mu is the mean overall miles per gallon. Alpha I is the ith engine size main effects. Gamma J is the jth motor oil type main effects. And alpha times gamma ij is the interaction between engine I and oil j. And together, we should have that the summation of I equals 1 to 2 of alpha I is equal to the summation of j equals 1 to 3 of gamma j is equivalent to the summation of I equals 1 to 2 of our interaction effect, which is equivalent to the summation of j equals 1 to 3, also of our interaction effect, which should be equivalent to 0. So now that we've set up our model, now we can move on to our hypothesis testing. So for hypothesis testing of one-way ANOVA model, we may recall that there was a particular order for the test to be performed. First, we did the overall F-test to determine if there's any difference between our factor levels. If that was significant, then we did our contrast and pairwise comparisons, all those t-tests, to compare specific levels of the factor. And when we did our t-test, we did the Tukey's test. So when we look at our testing comparisons from 2, again, if that overall test from 1 is significant, we called that Fisher's protected method. So one more time. So when doing a one-way ANOVA model, we first do our overall F-test. If that's significant, we then do our contrast and pairwise comparisons using Tukey's method. Following this process is called Fisher's protective method. Now we're going to do a similar fashion of doing our two-way ANOVA model. And to help you out, I'm going to make this into a little bit of a flow chart. So step 1, we are going to do the overall F-test for the model. If that test is not significant, we're going to stop. Because if our factors don't have an effect on our response, then it's not going to be useful for us, so we need to move on and look at other possible factors that influence our response. If it is significant, then we are going to do step 2. And we are going to do an F-test for the two-way interactions. And we haven't talked about this before, but basically what it is we'll perform a partial F-test. If this F-test is significant, we will then do pairwise cell comparisons to see what factor level combinations produce the best results. And once we have that information, we'll stop. If our F-test for our two-way interactions is not significant, then we'll do the F-test for our main effects. And so for this, for each significant main effect, we will do a contrast on that main effect to see what level of that main effect is most effective and influencing our response. And then once we're finished with that, then we'll stop. Now, at this point, you may be saying, well, what happens if none of the main effects are significant? If that was the case, where none of our interaction effects are significant and none of our main effects are significant, the overall f-test would have been proven to be insignificant. So we're not going to have the case where the overall f-test was significant, but steps 2 and 3 weren't significant. So let's go into this a little bit more thoroughly over the next few slides. So first, again, you test the model. For this, our null hypothesis is going to be mu ij is equal to mu equal for all ij. The alternative hypothesis is that at least one mu ij is not equal to the others. Or equivalently, we could write that our null hypothesis is mu or yijk is equal to mu plus epsilon ijk, and the alternative is yijk is equal to mu plus alpha I plus gamma j plus alpha times gamma ij plus epsilon ijk again. So this would be essentially 0, showing that the main effects and overall effects have no effect. So we will reject our null hypothesis if f, which would be equal to our sum of squares of our cells divided by the degrees of freedom of the cells, all over our sum of squares error divided by the degrees of freedom error, which, you know, we can simple down to the mean squared cells over the mean squared error, is greater than f alpha for the degrees of freedom cells, comma, the degrees of freedom error, where our sum of squares of cells are equal to n times the summation of ij for the quantity yij dot bar minus our overall grand mean quantity squared, with degrees of freedoms for the cells of a times c minus 1. And SSE is equivalent to the summation of ijk for the quantity yijk minus yij dot bar quantity squared, and the degrees of freedom for the error is a times c times the quantity n minus 1. An exercise for us: with any two-way data set, we can show numerically in JMP that the cell means test on this slide equals the overall f-test from chapter 6. I'm going to let you guys do this on your own. Now let's continue to say our next steps. So we just finished step 1, and we can say if our model is significant, we'll now test for our interaction effects, step 2. So testing for our interaction effects. For this, our null hypothesis would be alpha times gamma ij equal to 0 for all ij versus the alternative where at least one alpha times gamma ij is not equal to 0. We will reject our null hypothesis if f equal to our mean squared of our interactions divided by our mean squared error is greater than f alpha for our degrees of freedom for our interaction, comma, our degrees of freedom for our error, where our sum of squares for the interaction is n times the summation of ij times the quantity of yij dot bar minus the overall grand mean and quantity minus the quantity of yi dot bar minus the overall grand mean minus the quantity y dot j dot bar minus the overall grand mean and quantity squared, and our degrees of freedom for our interaction effect is a minus 1 times the quantity of c minus 1. And if our test for interactions is significant, the test for contrast or pairwise, we perform the test for contrast or pairwise comparisons for our interactions. If our test for interactions is not significant, then we move on to step 3, which is testing for our main effects. So part 3A for testing for our main effect of factor A, because we'll test factor A and factor C. Our null hypothesis for factor A would be alpha I equals 0 for all I versus the alternative where at least one alpha I does not equal to 0. The rule will be that we will reject the null hypothesis if F equal to our mean squared for our factor A over our mean squared error is greater than F alpha for our degrees of freedom for factor A, comma, our degrees of freedom for the error, where our sum of squares for our factor A is C times N for the summation of I times the quantity of yi dot dot bar minus our overall ground mean and quantity squared, and our degrees of freedom for our factor A is A minus 1. If the test for the main factor A is significant, we can go ahead and test the contrast or pairwise comparisons for factor A. Regardless of that, we are still going to want to test the main effects for factor C. So for this, our null hypothesis is gamma j equal to 0 for all j versus the alternative where at least one gamma j is not equal to 0. We will reject our null hypothesis if F is equal to, where F is equal to, our mean squared for factor C over our mean squared error is greater than F alpha for degrees of freedom for factor C, comma, degrees of freedom for error, where our sum of squares for factor C is A times N for this times the summation over J for the quantity Yiji, wow, that's twice in a row, Y dot J dot bar minus our overall grand mean quantity squared for degrees of freedom for our factor C is C minus 1. If the test for main effects of factor C is significant, we'll then go ahead and test our contrast for pairwise comparisons for factor C. Woo, that's a lot. Okay, so I can understand if the previous 3 slides were a bit confusing. You're like, okay, I understood the flow chart. Well, let me show you how we put this all together. We do it in an ANOVA table. Yay! All right, so taking a look at our overall two-way ANOVA table. Under source, we have model in between cells. That's our step 1. That's that first F statistic we are going to look at. That's that overall F test. If that value is not significant, we stop. We look no further. If it is, then we're going to continue down and look at our interaction effects. And so this is going to be our interaction effect F test. So step 1, look at the overall F test. Step 2, if that's significant, we'll look at our interaction effect F test. If that's significant, we will then explore the interaction effect by doing those pairwise comparisons. If it's insignificant, we move on to step 3 and we examine our main effects. So these are the main effect F test, and I'll try to squeeze this in. And we will examine both of those individually. If factor A is significant, we'll go and do the pairwise comparisons. If factor C is significant, we'll look at those pairwise comparisons. If either of those are not significant, we don't examine them. So at this point, in the notes, it says we should go ahead and complete the exercise with the two-way ANOVA examples on eCampus. And this example does include all the jump instructions and screenshots. I'm not going to do that in this video. I'm going to do that in a separate video, and I'm going to continue on and talk about our three-way ANOVA table. And you'll see how this very easily extends to what we've already done so far. Okay, so taking a look at our three-way ANOVA table and for those higher. So data sets and the corresponding analysis are not limited to one or two qualitative factors. We can easily expand the two-way ANOVA methods to analyze this data. We're going to cover three-way ANOVA in class in the next few slides, but 4, 5, and all the way up, way ANOVA tables are going to follow pretty much the exact same pattern. So first off, let's take a look at the three-way ANOVA model. So the three-way fixed ANOVA model is y ijkl is equal to mu plus alpha I plus gamma j plus delta k plus the two-way interaction effect of alpha times gamma ij plus alpha times delta ik plus gamma times delta jk plus the three-way interaction effect of alpha times gamma times delta ijk plus epsilon ijkl, which is equivalent to mu ijk plus epsilon ijkl. For I equal to 1, 2, all the way to A, j equal to 1, 2, all the way to C, and k equal to 1, 2, all the way to D, and L equal to 1, 2, all the way to N, where yijkl equals the Lth observed response from the combination of the ith level of factor A, jth level of factor C, and the kth level of factor D. Mu ijk is the mean response of the population with factor A at level I, factor C at level J, and factor D at level K. Epsilon ijkl is the difference of response L from its population mean, mu ijk. And the A times C times D times N unobservable epsilon ijkl are a random sample from a normal distribution with mean 0 and variance sigma squared. And to keep continuing on, mu is the summation for ijk of mu ijk over A times C times D and is the overall mean response. Alpha I is the main effect of factor A at level I. Gamma j is the main effect of factor C at level J. And delta K is the main effect of factor D at level K. At this point, you may be wondering when you're seeing factor A, factor C, factor D, you might be wondering why we didn't do factor B. That was a decision made by statisticians a long time ago where they thought it was going to be confusing to have factor A and factor B. I don't actually know much beyond that they thought it was confusing for some reason, but we're just going to roll with it. So, moving on. So, alpha times gamma ij is the two-way interaction effect of factors A and C at levels I and J. Alpha times delta ik is the two-way interaction effect of factors A and D at levels I and K. And gamma times delta jk is the two-way interaction effect of factors C and D at levels J and K. And finally, alpha times gamma times delta ijk is the three-way interaction effect of factors A, C, and D at levels I, J, and K. And these 8 bullet points here all imply that the summation of I equals 1 to A for alpha I is equal to the summation for J equals 1 to C of gamma I is equal to the summation of K equals 1 to D of delta K is equal to 0, and that the summation of I equals 1 to A of alpha times gamma ij is equal to the summation of J equals 1 to C of alpha times gamma ij is equal to 0, and that alpha I the summation of I equals 1 to A for alpha times delta IK is equal to the summation of K equals 1 to D of alpha times delta IK is equal to 0. And the summation of J equals 1 to C of gamma times delta JK is equal to the summation of K equals 1 to D of gamma times delta JK is equal to 0. And then the three-way interaction effect, the summation of I equals 1 to A of alpha times gamma times delta IJK is equal to the summation of J equals 1 to C of alpha times gamma times delta IJK is equal to the summation of K equals 1 to D of alpha gamma delta IJK, and it is all equal to 0. Woo! Now, for the hypothesis testing for the three-way ANOVA, I am going to follow and create a very similar flowchart that you saw for the two-way. So once again, to start off, we do the overall F-test for the model. If that test is not significant, we stop. If it is significant, then we move on to step 2 and we do the F-test for the three-way interaction. If that is significant, then we look at the pairwise comparisons. And once we find the levels of the three-way interaction that are the best or optimal, then we can stop. If the three-way interaction is not significant, then we will do an F-test of the two-way interactions. And for this, for each significant two-way interaction, we would perform the pairwise comparisons. If our test for our two-way interactions is not significant, we then would complete the F-test for our main effects. And for each significant main effect, we would do the contrast on the main effects. Now, there is one more step to add in. So, going back to step 3, we were saying that if the F-test for the two-way interaction is significant, we would do the pairwise comparisons for each of our two-way interactions. What we would also do is we would also do the F-test of the main effects for all main effects not significant in the two-way interaction. And so what I mean by that is perhaps factor A and C were found to be significant, but A and D and C and D were not. So that would tell us that we should test the main effect of D and look at the pairwise comparisons for A and C. Okay, so last slide is to take a look at our three-way ANOVA table. So very similar to what you've already seen. Under source, we have the model between cells. That's going to be our step 1. It's that overall TEF test. Next, if that is significant, we would take a look at our two-way if step 1, our overall F test is significant, we would then take a look at our three-way interaction effect and see if that's significant. If it is, we would then complete our pairwise comparisons. If it's not significant, then we would start looking at our two-way interactions. And if none of those are significant, then that's when we start looking at our main effects, F test. And if those are significant, then we take a look at the contrast that just involve those main effects that are significant. And that's about it. If we wanted to extend for four-way, five-way, you can kind of see the pattern. We first do the overall F test, and then we take a look at the interaction effect that is of the highest value. So if it's a five-way ANOVA table, we'd start by looking at the five-way interaction. If the five-way interaction is not significant, then we take a look at the four-way interactions, then the three-way, then the two-way, and then we take a look at the main effects. At this point, the last note of these slides is asking us to complete the three-way ANOVA examples on eCampus. I am going to do that in a video, but I'm not doing it in this notes video. I'll do it along with the two-way ANOVA examples. I'll probably do one video for the two-way and one video for the three-way examples. Okay, class, so that's it. That's the end of your theoretical notes and the material covered on your final. It was a pleasure having you in class this semester, and I hope we can meet again in our future. Have a good night.